Fundamentally, digital systems are just analog systems being used in a particular way. We now know that logic gates are made using FETs, and in particular, the inputs and outputs of logic gates are just voltage waveforms, and they don't necessarily take the values 0 volts and 5 volts. If we go to the datasheet for a logic gate, we're going to be told a set of 4 numbers. V output low, V input low, V input high, V output high. The logic gate, if it's outputting a logic 0, is guaranteed to be outputting a voltage less than V output low. So V output low is the largest voltage such that this logic gate will output a low value. Similarly, V output high is the lowest voltage that the logic gate is guaranteed to output if its output is supposed to represent the number 1. For the same gate, the input is treated as a logic 0 provided it is lower than V input low, and it's treated as a logic 1 provided its input is higher than V input high. The noise margin is the region between the V input high, V output high, and between V output low, V input low down here. It's called the noise margin because if we consider the output of one gate going into the input of another gate, and realizing that every system's noisy, the wire connecting from here to here can pick up noise from elsewhere. The supply rail can also induce noise on the output, etc. So if, for example, the output of this logic gate is supposed to be a logic 0, then that means it's going to lie somewhere within this region down here. For the input over here to recognize that it's at a logic 0, the voltage must be below V input low, which means that in the worst case, the output from the first logic gate might be at this level here. We need the input to this logic gate to be lower than this level here, which means we've got this much room for margin for error. So provided the noise is smaller than the value here, then this logic gate will recognize that the output of the logic gate before it is a logic 0. And the same argument applies for a logic 1. In an analog system, as the signal propagates through resistors, capacitors, transistors and whatnot, you get more and more noise. This does not happen in a digital system because logic gates tidy up the signal. The input might be close to, say, 1 volt in this example here, but the output is then guaranteed to be above 4.5 volts. So even if we had noise of half a volt riding on the input here, we get rid of that at the output here. Every single logic gate is cleaning up the signal, which means digital systems are very robust to noise. Basically, this is why we switched over from analog computing to digital computing. In analog computing, the noise just causes too much problems. Digital computing, you essentially get rid of the noise problem completely. The reason logic gates tidy up signals can be explained from their voltage diagrams here. Take the humble inverter made using 2 FETs, N channel on bottom, P channel on top. An ideal inverter has got this response in green. So here's the input voltage, here's the output voltage. If the input voltage is anywhere between 0 and 2.5 volts, the output voltage should be 5 volts. And if the input voltage is from 2.5 volts to 5 volts, the output voltage should be 0 volts. That's an ideal inverter. In practice, we've seen using LT-SPICE simulations, it looks something like the red curve here, maybe even steeper. And it's because this curve is so steep in the middle and thus flat at the ends, we get very good robustness to noise. Specifically, we see that if we want the output to be very close to 5 volts, the input can actually be very far from 0 volts and will still have a very nice tidy output signal here. So lots of noise down here produces a very small amount of noise at the output. The same occurs if the input is high. If we want the output to be very clean, very close to 0 volts, then it suffices for the input to be anywhere as low as, say, 3 volts, 3 to 5 volts. So we can have lots of noise on the input and get very little noise on the output. Every single logic gate is tidying up the signal. It squashes the noise down into a very small region because the transfer function is very steep in the middle, very high gain if you like, and that gives us very flat, smooth sides here, which means large changes at the input produce only a very small change at the output. We get robustness to noise.